Example 3. Again, we have to determine whether the improper integral diverges or converges and evaluate the integral if it converges. We'll have the integral from 1 to infinity of 4 over the fourth root of x. Technically, I could use that theorem on the last page for this problem because I could rewrite this as 4 times the integral from 1 to infinity of dx over, and this is x to the 1/4. That means my p is equal to 1/4. That is a number that is going to be less than or equal to 1, so I know that I'm going to diverge. But if we didn't realize we could use a theorem, we'd have to evaluate it just like we did in examples 1 and 2. So let's go ahead and do that for practice. To begin with, I have to rewrite this as a limit statement. The limit as c goes to infinity of the integral from 1 to c. And I'm going to rewrite this as 4. And instead of writing x to the 1/4 in the denominator, I'm going to bring it up to the numerator and write it x to the negative 1/4. Now use the power rule to evaluate the limit as c goes to infinity, and this is just going to be 4. If I add 1 here, it's going to be x to the 3/4, and then divide by 3/4, or you can think of it as multiplying by the reciprocal, which is 4/3. And this gets evaluated from 1 to c. Multiply those numbers first, and then plug in the limits of integration. So 16/3 x to the 3/4. If I now plug in the limits of integration, I end up with 16 over 3 times c to the 3/4, and then minus 16 over 3 times 1 to the 3/4, but 1 to any power is just 1, so we're just going to say minus 16 over 3. So what is this? When c goes to infinity, what is c to the 3/4? Again, if you forget, just grab your calculator and let your calculator assist you here. Instead of writing c to the 3/4, we can keep that 16/3 in here if we want to, but we're just going to make it x raised to the 3/4 power. So when x is raised to the 3/4 power and we're approaching infinity, where are the y values going? Well, they're increasing without bound, so we know that this would equal infinity, and infinity minus 16/3 is going to be infinity. And then just like we said before, what this means for us is that the integral diverges. What about number 4, the integral from negative infinity to 0 of x over e to the 4x? First, I have to rewrite it without negative infinity. Write it as a limit statement. The limit as c goes to negative infinity of the integral from c to 0. And then I'm going to rewrite this as a product because this is not a u sub, so it's most likely integration by parts, and that means we need to have it as a product. So x e to the negative 4x. Well, how am I going to integrate x e to the negative 4x? Well, in order to integrate this when it's algebra and exponentials mixed, remember what we needed to do is integration by parts. And when we're using integration by parts, we use Lie to assist us in figuring out what should be u. Well, I don't have a log, I don't have inverse trig, but I do have algebra, so my algebra is going to be my u. Well, if u is equal to x, I know that I can take that derivative down to 0, so I can use the tabular method. Using the tabular method, u is x, I take the derivative of x is 1. Take the derivative again, the derivative of 1 is 0. And then I assign the signs, so positive, negative, and I stop because 0 is neither positive nor negative. dv is the other part of it, and that's that e to the negative 4x. Remember, negative 4x is linear. So when I'm integrating it as an e to the u, but I have to multiply by the reciprocal of the coefficient of the x term. So I have to multiply it by the reciprocal of negative 4, which is negative 1/4. So we have negative 1/4 e to the negative 4x, integrate again. Negative 1/4 times the negative 1/4 is a positive 1/16 e to the negative 4x. Now put it in your limit. So we say the limit as c approaches negative infinity of, and then it's x times negative 1/4 e to the negative 4x. So I'm going to write negative x over 4 e to the negative 4x, and then minus 1 over 16 e to the negative 4x. And this gets evaluated from c to 0. If I plug in those limits of integration, the limit as c goes to negative infinity of negative 0 is just 0, and 0 divided by 4 is just going to be 0, and then e to the 0 is 1, and then minus 1/16, and again e to the 0 there is just going to be 1, and then minus, this is negative c over 4, e to the negative 4c, and then minus 1/16 e to the negative 4c. Well, this is just 0, and that's just negative 1/16. And the limit as c goes to negative infinity of negative 1/16 is just going to be negative 1/16. But over here, well, this is going to be negative infinity times a negative, which is positive infinity. And then it's going to be an e to the positive infinity, which is infinity. And then minus, and this is going to be 1/16 times e to the infinity, which is going to be infinity. Well, that's infinity minus infinity, and this is that bad indeterminate form. I need to do some work to figure out what this is going to be. So I'm going to rewrite it because my negative 1/16 is all done. And this is the limit as c goes to negative infinity of. Now notice, I have an e to the negative 4c and an e to the negative 4c. I am just going to factor out an e to the negative 4c. If I factor out an e to the negative 4c, I'm left with a negative c over 4 minus 1 over 16. Now if I try to take the limit, and there should have been a minus sign here, it should have been negative 1/16 minus. Now if I try to take the limit, well, this is going to be infinity, and this is going to be times infinity. Well, infinity times infinity, not an indeterminate form, we know that that's equal to infinity. And negative 1/16 minus infinity is negative infinity. So since I got negative infinity, what does that mean? That means that my integral diverges. Number 5. The integral from negative infinity to positive infinity of 1 over x squared plus 1 dx. The first thing I need to do is rewrite it as a limit statement. So I need to not have negative infinity, and I need to not have positive infinity as limits of integration. So I know I could choose a number, any number between negative infinity and positive infinity. I'm going to choose 0. So we're going to split this up as the integral from negative infinity to 0 of 1 over x squared plus 1 dx plus the integral from 0 to infinity of 1 over x squared plus 1 dx. Then rewriting it, this becomes the limit as c goes to negative infinity of the integral from c to 0 of 1 over x squared plus 1 dx plus the limit, and since I'm already using the letter c, I have to use a different letter. Let's choose d, as d approaches positive infinity of the integral from 0 to d of 1 over x squared plus 1 dx. Well, can I integrate 1 over x squared plus 1 dx? Yes, it's basic form, it's just the inverse tangent. Recall with inverse trig, we identify a, u, and du. U squared would equal x squared because that's the variable. U is equal to x. Du is equal to dx. Perfect, that's exactly what you have. A squared is equal to 1 because that's the constant. Therefore, a is equal to 1. So now we integrate, and we know that this is equal to 1 over a. Well, 1 over 1 is just 1. I don't need to write that. And then times the inverse tangent of u over a. Well, x over 1 is just x, and then the first time around this gets evaluated from c to 0, and then plus limit as d goes to infinity, same thing, it's the inverse tangent of x, and this gets evaluated from 0 to d. If I plug in those limits of integration, I have the inverse tangent of 0 minus the inverse tangent of c, and then plus the limit as d goes to infinity of the inverse tangent of d minus the inverse tangent of 0. What's the inverse tangent of 0? Well, the inverse tangent of 0 is just 0, so I don't have to worry about this term at all because it's 0. Then I have to figure out what is the inverse tangent of c. Well, when c is going towards negative infinity, what's the inverse tangent of negative infinity? Well, let's look at the graph. If you were to think of the graph of the inverse tangent, it looks similar to f of x equals x to the 1/3. It looks like this. It has a horizontal asymptote up here at y equals pi over 2, and it has a horizontal asymptote down here at y equals negative pi over 2. Therefore, when I'm approaching negative infinity, my y values are approaching negative pi over 2. So this is equal to the negative of negative pi over 2. And then, if you're looking at d approaching infinity, the inverse tangent of infinity, when you're approaching infinity, you're approaching positive pi over 2, so that's plus pi over 2. So you have the negative of negative pi over 2 plus pi over 2, which is just equal to pi. Since the limit exists and it's equal to pi, that means that your integral converges.